Okay, so in this video, we're going to look at Parseval's theorem. Okay, which we already saw for periodic functions in Fourier series, but now we're going to look at it for Fourier transforms. Okay, so what does it say? Well, it's going to look pretty similar, but with some differences to the previous Parseval's theorem for Fourier series that we saw. But we're going to integrate the magnitude of our function f of t squared. Okay, sometimes you might see this is called the energy of the signal. Okay, and this is going to be equal to this expression on the right. Okay, so you can see how they're pretty similar. Here we're integrating the magnitude squared of our function in time. Here we're integrating the magnitude squared of our function in frequency, the Fourier transform. Okay, and sometimes this is called the energy spectrum. Okay, so those are just some terms that you might see here and there. Okay, but this is Parseval's theorem. Okay, and it allows us to relate the energy of our signal in time to the integral of this energy spectrum and frequency. Okay, so this can be useful in much the same way that Parseval's theorem for Fourier series was useful. So let's prove it. Let's prove this. Okay, maybe some of these manipulations and techniques can be useful in other problems. So we'll just start with the left side. So we have the integral of the magnitude of f of t squared dt. Okay, now what can we do? Well, it's probably going to look pretty similar to our proof for Parseval's theorem for Fourier series. But we're going to write that magnitude squared. We know the magnitude squared of a complex number is just that number times its conjugate. Okay. And now I'm going to use the inverse Fourier transform formula, plug that in for f of t, that f of t with the conjugate. Okay, so this is our inverse Fourier transform formula. Then I'll just conjugate that whole thing. Okay, that's my f of t conjugate. All right. Now what can I do? Well, I'll actually perform that conjugation, and I'll bring the 1 over 2 pi outside of f of t, and the integral of f conjugate of omega e to the negative j omega t, right? When we conjugate this e to the negative j, or sorry, e to the j omega t, we get a negative sign in the exponent. Okay, and then d omega dt. Now what am I going to do? Now I'm going to flip the integrals. Okay, so now this one is going to be the d omega one, and the inner one will be the dt one. And so when I do that, I can bring this f conjugate of omega term out. And what am I left with? I'm left with the integral of f of t e to the negative j omega t. And now remember, I flipped these integrals. This is going to be dt and then d omega. Okay, so everything there looks good. And now what is jumping out at us? Well, look at this inner integral. All right, what is that? That's just the Fourier transform. That's the Fourier transform of f right there. Exactly the formula. Okay, so I'll just plug that in. F conjugate of omega, and now I just have f of omega, d omega. And now we use the same thing we did in the first step and say, all right, f of omega times f conjugate of omega, that's just the magnitude of f of omega squared. And there it is. So that's Parseval's theorem. Okay, and you can apply this to any Fourier transform pair that we've looked at so far if you want some practice, and verify that both sides of this equation actually do equal each other. Okay, so that's all I had for this video, and I'll see you in the next one.